Okay, welcome to this afternoon's session, everyone. As a reminder, I'm Mark Lindsay, I'm chairing this session, but of course, our keynote speaker for this session is Guillaume Caumon from the University of Lorraine, talking to us on automation uncertainty management in 3D geological interpretation and modelling from geometry to graphs. Take it away.
Thanks, Mark. Hi everyone, thanks for being here, and thanks for inviting me to give this presentation. As you can read from the title, I'm going to talk about automation and uncertainty management, mainly in 3D geological modeling. We'll be talking about maps quite a bit, but as we all know, as geologists, maps are just the intersection between the subsurface geology and the topographic surface. And instead of starting with a pretty picture on this slide, I put this quote from Thomas Chamberlain, who was a famous American geologist from the late 19th century, who had this very interesting paper about developing multiple hypotheses and to say that in science we should strive to provide every rational explanation to our observations and not just the best case scenario. And so what I'm going to talk about is mainly oriented towards that. And this is, of course, a joint work with many collaborators who are listed as co-authors here. So, okay. So, as geologists, we like to go on the field and we like to map what we see. And if I ask every one of you to map what you see here, you'll probably be able to draw a couple of fault traces and a couple of stratigraphic boundaries, and trying to make sense about how these faults connect. And we can see that already in the surface we have extrapolation issues, we have very sharp features that we can clearly see at very high scale, but we also have some ambiguities because the outcrop conditions are not so good. Maybe we should change the viewpoint, or we should do something better. And the next question, once we have done this work at the surface, is to try to determine and to tell what lies below the Earth's surface, and whether we can quantify the uncertainties about how to extrapolate these geological objects, faults, horizons, and the like in the subsurface. So the classical modeling strategy to do that, and we had some very nice examples this morning, is to interpret the structures, interpret the objects that we want to map, choose the objects that we want to map, and once we have interpolated and came up with a geometry, we might also want to perturb or to look at the uncertainty of this extrapolation. And so if we start by the interpretation from a set of drill hole data and log data, classical interpretation can be to determine stratigraphic sequences that we can label and that we can name. If we start from geophysical data, such as the queen type of geophysical data we can think about for structure is seismic reflection. And so this is a cross-section in the Gulf of Corinth. And if I give this image to you, you might come with something like this, or at least this is the interpretation that was made by Brian Taylor in his Geophysical Journal International paper. And this interpretation, as we know, can be tedious, can be time-consuming, and they call for a number of skills. So this is essentially the first thing. When I started to work in this area, we did not question this data at all. We said, okay, these are the data, and you have to create a 3D geometry from that. So to create a 3D geometry, you start from the labeled interpretation, so points in space, parallel lines, and first thing is to come up with a three-dimensional representation by triangulation, Delaunay or whatever, or wireframing, so associating parallel lines and coming up with an initial geometry. And that's still of common use in a number of applications, for instance, to report mineral resources. When you look at the detail, the outcome of this type of method depends a lot on where the points are, and you can have some very sharp features or kinks that are very artifacts about the data location, and probably these artifacts are not real. And so this led a number of people during the 80s and the 90s to develop interpolation or mesh smoothing algorithms. So starting from an initial surface to try to minimize the curvature or minimize the Laplacian of these surfaces by numerical optimization. And at the time, the computers were not very powerful, so some ideas was to use to represent every interface as a graph of nodes connected by triangles or squares, and to solve numerically or iteratively a minimization problem under constraint to try to have a smooth and nicely looking surface without, while fitting the data that we have. During the 2000s, the implicit modeling method came out. Actually, it was earlier, but again, because of computational requirement, it really became highly deployed during the 2000s. And here the idea is to say, instead of interpolating one surface or every geological surface one at a time, we are going to interpolate the surfaces as equipotential or iso-value surfaces of a 3D volumetric level set. And so there's been a number of formulations. I've put some references, and I'm sure there are people in the room who are very familiar, and we might have some further presentations about that in the rest of the conference. Among all these references, what changes a lot is what we define as a mathematical term to define what happens between the points, and also how we choose to represent on a computer this function by a set of basis functions which can be aligned on the data or which can be aligned on some interpolation mesh. But I'm not going to delve too much into that. And once we have this initial geometry, what we can do is try to perturb the geometry, and we've seen some nice examples this morning. So this can be done on the stratigraphy, this can be done on the faults, and with sampling strategies and using some geostatistical simulation, it's possible to generate various possibilities about where the geological interfaces can be, and sample that part of the epistemic uncertainty that we've been discussing. We might argue about the term whether this is epistemic or stochastic, because in the end this is just sampling probability distributions. So to me this is just a stochastic process, but we can further argue or discuss on this term. And so that's it. So this is where we are right now. So what are we missing with regard to geological uncertainties? So let us get back to the Gulf of Corinth, and let's have a look at a larger look at the seismic section. As you probably know, if I give this image to every one of you, I will end up with not just one interpretation, but maybe that interpretation or this interpretation. And we already had this quote that 5 geologists give 10 interpretations. And so there is quite a lot of uncertainty, and this topic has been investigated quite extensively by the team of Clarbond. And so she has very nice papers. She and the group have very nice papers on that. So I will not further elaborate there. On top of that, if we zoom in one particular area of interest in the seismic data, we might see very parallel reflector, and we might interpret parallel strata. But if we zoom very deeply, we know that strata are not slabs. Strata are clinoforms at many nested scales, and they are separated by a lot of unconformities at many spatial and temporal scales. And this has been known in sedimentology for quite a while. So, so we are limited also by the bandwidth and the resolution of the seismic data, or whichever data or whichever observation that we have. And so at some point we have to choose what is the scale that we want to represent in our model and what is the scale that we want to interpret. So we have a whole set of new questions now. What are the acceptable scenarios among these various solutions that we've seen? Could we make interpretation a bit more reproducible? So this has been touched upon also this morning with NLP talk about, can we archive the knowledge of interpretive knowledge that's been put into this result, which in the end is just an image with some labels or maybe some vector structures. And we also have the fundamental question about which detail matter, and that depends a lot on the model purpose. What do we want to do with this model? Because we want to have a map, but some features of the map may be completely meaningless for some application and extremely important for some other applications. So let's get back to the sources of uncertainty that we have. We have measurement errors, right? We may be wrong about the measured value, about the position, the exact location. We have incomplete coverage. We have limited resolution of the data. We have all sorts of averaging that we have from the measurement devices. And we can also have intrinsic lack of contrast about what we want to measure. Maybe we are after the geological age, but there's no petrophysical contrast for the particular type of measurement device or geophysical tool we are using. Each time we have data, there's always some kind of processing involved. So what type of processing? What are the fundamental hypotheses? What are the parameters of the processing algorithms? There can be quite a bit of subjectivity, either human subjectivity for the choices or algorithmic subjectivity, assuming that the parameters are Gaussian independent or identically distributed. Okay, these are mathematical assumptions that can all affect the results of the processing and the images or the more or less raw data or the processed data that we deal with. And the last source of uncertainty, which is what I call epistemic uncertainty, is really into the concepts. What are the interpretive concepts that we put in there? Are they appropriate? Are they complete? Quite often they are not. Are they explicit? So what happens in the back of your head when you draw a line or when you make a reasoning? One of the interesting findings of Clarbon, by the way, was that for drawing geological cross-sections or interpreting geological cross-sections from seismic data, the best results and the most accurate results were made by using balanced approaches. So using some balancing and some well-known structural geology approaches that reduced a lot the uncertainty. Okay. And the last question is reproducibility, which I already discussed. And so we need to integrate all these type of uncertainties together to come up with our overall objective of coming up with many rational explanations about our observations. So what I'm going to talk mainly are the two last parts. I will not talk too much. I'm not a geophysicist or a data metrology specialist. I will mainly talk about the measurement and the geological concepts aspect to present some of the things that we've been doing on the topic of fault networks, and I'll touch upon also some aspects of stratigraphic architecture. So for fault uncertainty, the first item is the identification of the evidence. And so for that, there's been a great deal of approaches in geophysics to automatically identify or detect faults from reflection seismic images. So this is work done by my colleague Qinming Wu, who is at USTC in Hefei in China. And so the idea is to come up with, generate randomly a layer cake of strata, apply some geometric operator to fold the strata, to fault the strata, and to generate a large database sampling many different fault configurations, many fault orientation, displacements, and to do that very locally in order to create a large training database for convolutional neural network and treat the problem as a classification problem. So at each point, what he's after in this FaultNet 3D method is there a fault or not, and what is the fault orientation, and what is the likelihood of a fault. So this is a kind of a probabilistic classification approach. And so in the end, mapping the result of this convolutional neural network gives a fault likelihood attribute. As you can see, this likelihood is a bit thick, so there is some uncertainty in there. Actually, maybe you do see faults that have not been classified in there, but let's assume that we can trust this result and that the training database is rich and representative enough to make predictions about the likelihood of fault existence. What we've been working on with my PhD student Fabrice Tati-Moukati has been to use stochastic point processes, so to simulate possible structures based on this likelihood approach. So these are just a couple of scenarios with a particular choice of parameters for this stochastic point process. What the model consists of is very simple. It's a geometric structure with a set of segments, which are all characterized by a geometry, by a size, by an orientation. So this is only two-dimensional at this stage. It's also characterized by a well-defined probability distribution, which is a Gibbs distribution. So it's the exponential of an energy, which consists of mainly two terms: a data energy, to say whether a particular fault segment is compatible with the likelihood. So is it located in an area where the convolutional neural network thinks a fault may occur? And it's also characterized by an interaction energy, and this is really the tricky bit, because this will constrain the fault shape and how these segments can arrange in the space. So this is a prior geological term that we are trying to characterize with geometrical criteria. So what Fabrice has been using as a mark point process is the Candy model, developed completely independently and before by my colleague Radu Stojka, where the idea is to say the segments are not independent one from another. We want to, we have an overall segment density in the model. We have some parameters to characterize how many free segments exist, so isolated segment or isolated faults, if you like. How many singly connected segments exist, where you have two segments that are in continuity one from another, and that can create a curved object. Doubly connected segment, where you have a chain of segments. And you also have some interactions, which we call the shadowing interaction, that we may or may not authorize in the model. And so all of this energy term is defined by this set of constants. So these gammas and betas are the model parameters. And if we have some data, we can also count in the domain the number of these configurations, and that way we have a well-defined probability for this model. So I will not go further into the detail, but essentially the simulation uses the Monte Carlo process. So it's trial and error simulating segments, working well with the proposal distribution to make sure that the acceptance probability remains reasonable. And this is one of the, I would say, the best realizations obtained by this model. And if we do that over and over again, we can also compute the a posteriori estimates, so generate many realizations and compute the posterior probability, which obviously is consistent with the initial likelihood and consistent also with the prior terms or the mark point process definition. You see that there may be some artifacts, so the posterior density is lower in some areas, but overall there is a good fit and there is an overall reduction of uncertainty because of the knowledge that is brought by the prior model. What can be done from there? It's possible to run the scenarios. So if you have a reference interpretation, so this one was obtained by the ridge regression of the fault likelihood, so it's a deterministic solution. For any given segment configuration, you can try to see whether it's compatible or not in terms of spatial statistics. You can compute the distance to the solution, to this particular scenario, and the distance to the reference solution, and you can compute the probability density function, the PDF, of these two distance fields, and that's called the empty space function in spatial statistics. And so looking at the probabilities of two solutions, or the probabilities of an ensemble of realization, which is highlighted in gray here, you can check the influence that some parameters, the parameters of the statistical model have on the result to try to reproduce or to mimic what has been done by a reference solution, be it obtained by an algorithm or be it obtained by an expert interpretation. The second part, that now that we have identified some objects or some data, so I've just taken this as an example, the identification of faults on a seismic section. The second problem is the association of the evidence. So now let's take the example of some boreholes. If you have borehole images, you can probably identify some fault location. You may also be able to identify some intervals that have undergone hydrothermal alteration, which could be an indication of the proximity of a fault or paleofluid circulation. And obviously, you may also have some stratigraphic horizon, and if you have a vertical shift between two nearby horizons, this could be an indication of the existence of a fault between these two data points. And so again, this is one out of many possible rational explanations of these observations. And how can we try to generate that on a computer? So this problem has been explained or has been considered in the 90s by Brett Freeman and has been formalized recently by my PhD student Gabriel Godefroy as a graph generation problem. So we have every evidence which is represented as a node, and every possible scenario can be represented as a graph that associates the nodes together, and when two nodes are associated, they belong to the same fault surface. So I will skip that, but essentially we have data, we have some associations. So to generate this graph, we will start with an association likelihood. So we need a way to assess the probability for these two nodes to be associated together. And then we enter the next questions about how to compute that. So we can use simple geometrical rules, which was what Gabriel Godefroy did during his PhD. And what Amandine is doing right now, spoiler, is using machine learning for that. So she has a poster, so I will not spoil much more what she's been doing. And you can have a look and chat with her. One of the nice aspects, though, is that you can look not just at whether two pairs of data or two evidence are associated, but three evidence or four evidence using some of the multiple point geostatistics concept that also came up for another type of problem. Once you have this graph of associations, you can sample it. And so, again, I will not go too much into the detail and come up with various scenarios about various faults separating and associating all the data together. So, second part of the talk, and I only have 4 minutes now, probably. So, everybody's afraid. I will not talk too much about stratigraphic architecture. I will just have one slide. From Paul Baville, where the idea is to kind of do the same, so identify the evidence along the boreholes, and using a signal association algorithm called dynamic time warping, which we have tuned and adapted to the stratigraphic correlation problem, to test various correlation scenarios. And so the idea of Paul's thesis, among others, was to have a look at the sediment transport direction and to translate that as a correlation rule to associate various facies that would be located at different paleo water depth, and to test what could be the transport direction. And as a screening effect, he used biostratigraphy, so this was not part of the input, so the colored intervals in blue correspond to the biostratigraphic data, and that way he could screen the scenarios and try to come up with the most likely, at least if everything else is correct, the most likely transport direction. One of the big challenges, though, is to manage the interaction. So can we merge the thing we do in terms of stratigraphic correlation with the things we do with faults association? Because if we have a fault between these two wells, the problem will become much more complex. We need to have a look at the fault activity through time and how it could affect the correlation. And this is still an open problem to the best of my knowledge. So to conclude, I think framing the problem of geological interpretation and modeling as an object detection, association, and modeling exercise is very interesting. We've seen examples for faults in stratigraphy, but we're also working on karsts and on alteration halos, trying to jointly model the alteration and the location of the driving structures, still using point processes and distances and that kind of stuff. And I think progress to be made in this area can come from a combination not just of AI. By the way, thanks for inviting me, because I think I only touched very marginally to AI at this point, but also for good old and hopefully some new geomodeling and geostatistical approaches. If we want to close the loop, we need to also address two types of problems. One is the discretization and the level of detail. So if we want to loop back to the geophysical data or to loop with the application of the flow data in this example, we need to translate the geometry of structures into fields of heterogeneities, and that includes telling or controlling how much we approximate the geometry, because at some point we always have to find a trade-off between the level of accuracy and for the physics and the level of accuracy for the geometry. And the next challenge is also to navigate this complex parameter space made of geological objects. We have gradual deformation, we have transdimensional and reversible Monte Carlo Markov chain methods that allow to change these objects. And so this is just some animation to illustrate that. With that, I would like to thank you for your attention, and thanks to the sponsors of the Ring Consortium, which is, I guess, many organizations in this room are sponsoring, and we are open to other sponsors. Thank you very much.
Thank you very much. Fascinating talk. So opening the floor to any questions.
Thanks for the amazing talk. I have a general question about 3D geological models. How do you evaluate accuracy of the 3D model?
It's a very good question. In classical machine learning, you separate your data set into training and then test, and you evaluate the accuracy with test. In 3D geological modeling, we've been a lot towards the engineering part, and so we tend to stuff all the data that we have as a model, and then we make the prediction, and the only validation is drilling new data or doing something else. But it's really where we can always remove some data, but it will be extremely difficult to defend and to say someone, okay, you invested 1 million to drill this borehole, and we are not using it to build the model just to check that our model makes sense. It's a difficult case. But I agree we should work on the validation. The things on the... So I would say there's the validation with the data. The validation also can be statistical. So this type of thing can be also very interesting, because you can also compare with some analog data set in terms of spatial variability, in terms of features and that kind of thing.
Thank you.
Thank you very much for your excellent talk. I have a question about the part you're talking about the graph and the faults, right? So I think that one you prepare for the, convert from the fault to the graph. Actually, it's something probably you're gonna prepare for the graph neural network data burst or something. So my question would be like, within your graph, like how many nodes you're gonna have?
Can you say that again?
Oh yeah, I mean the graph. So
yeah.
You convert the fault to a graph.
Yeah.
So how many nodes within your graph you're gonna have in a single data?
Yeah, right now we've tested with relatively small data sets,
yes.
So a couple of 100 nodes, I would say, something that, or
100 nodes in the data set, or like in a single data?
100 graph nodes.
Graph node.
Yeah.
In a single graph, or like in a single graph?
Yeah, I mean, all the data are nodes of the graph,
yes.
So we have, say, a couple of 100 data points, so or false evidences, and each one is translated into a graph, and then this graph can be also split. I did not go into the detail, but this graph can be split depending on, say, the orientation. Like if you have north-dipping faults and south-dipping faults, unless you know you are in a high straight slip area where you can have a fault that goes that change deep. You can also split that into two separate subgraphs to restrict and reduce the complexity of the problems.
Yeah, that's exactly, because like where the if you are doing like working in a network, if you know this too much, then the adjacent metrics will be increasingly, crazily.
It's
So,
NP hard. Yeah.
yes, so I'm just curious about like the number of nodes like you mostly gonna recommend it or like in your work, like what is the recommended value you're gonna choose, like ask for the graph?
Yeah, I mean, we are, with these problems of association, we are very quickly hitting the complexity problem, because we've made complexity analysis, and for the fault association, it's given by the Bell number, so it increases very, very fast. In some statistical analysis, they are using the Hammer-Stickley fault theorem to try to reduce and to transform the global problem into a local problem because you have screening effect. In image analysis, you can do that. In our case, I think we can do that, but we have to be very careful because it really depends on how regular our data are and whether we can reasonably use the screening effects to reduce the computational complexity of the problem. But you're right, I mean, it's a tremendously difficult challenge, and I think the best way is to address it, and we're working on that right now, is to use a divide and conquer type of approach, try to be multi-scale and integrate multi-scale into this type of problems.
Thank you very much.